idea what Cole's notes are. That's because I'm old. All right, so we're looking at polynomial graphs, and we're going to look up to quartic function, actually, not cubic, but quartic function, which means that the exponent will be to the fourth. All right, now our objective here, which is ideal in this class, is to be able to draw out these polynomial functions and put them on paper, but you get Desmos to help you do it. So that's the beauty of it. But you need to know how to do it. When you get to pre-calculus, you've got to be able to draw the graph without any technology, which we want to learn how to do right now so that when we get to the pre-calculus, it's not a big deal. All right. So first things first, what do I want to show you? Well, let's start with a line. I'm going to putz around here a little bit. This and this, and okay, first things first, y equals 6. All right, so that is a graph of a constant function. All right, and there is no x there, so it creates a horizontal line. All right, how many y-intercepts are there? There's 1. Where's the y-intercept? 6. How many x-intercepts are there? 0. All right, one of the things that we do not know anything about yet is what we call end behavior. Now, end behavior is what quadrant does the graph start in on the left, and what quadrant does it end in on the right. So if you're looking at this particular graph, which quadrant does it start in on the left? 2. Which quadrant does it end in on the right? 1. The end behavior is written in Roman numerals. So for a constant function, y equals, and a just represents any value, any numerical value. The end behavior from it will be 2 to 1. Now it doesn't matter if it's y equals -6. Just down here, still gives me the same line. The only thing changes is your y-intercept. There are no x-intercepts on this. It does not cross the x-axis. It only crosses the y-axis. This is called a constant function. Okay? We change this away from a constant function by adding an x to it. So, for example, I have y equals x minus 6. All right. So, looking at this graph right now, first of all, how many x-intercepts are there? 1. So that's the other thing that we need to really hammer out is the x-intercepts, okay? All of them are going to have a y-intercept. The y-intercept is going to be the constant in the equation. Well, where's the constant in the equation? It's the value on the equation that does not have a variable attached to it. So there's no letter on it. So in this case, -6 is your constant. That is always going to be your y-intercept in a polynomial function. It will be the numerical value at the end of it that does not have an x on it. That is your y-intercept. How many x-intercepts on it depends on the type of graph it is. Okay, this is a linear function. It has 1 y-intercept, 1 x-intercept. Where does it start? What's the end behavior for this guy? 3 to 1. Now, 3 to 1 is correct if I have a positive slope. If that slope becomes a negative slope, now what is the end behavior? 2 to 4. So depending on what the a value is. Now the a value in any polynomial function is always found in the leading, in front of the x with the highest exponent. Let's put it that way. The x with the highest exponent. Now we're going to call that degree. All right. So a couple of things that we need to know. 2 to 1, that's what we call end behavior. Spell it the British way. All right. If I have a linear function, the a value is in front of the x. What is the exponent on this x? 1. The degree of this function, another new word for you. the degree of this function is always the highest exponent. In this case, it's 1. So the degree of that function is 1. There are 0 turning points for either one of these two graphs. Means little to you at the moment, but I'll show you why in a second. Okay, so the next graph we're going to look at is a degree of 2. The general equation for this. All right, when looking at the general equation, y equals ax squared plus bx plus c. What's the y-intercept for this equation? C is. Awesome. It's the constant. It's the value right there that doesn't have the x. What is the degree of this equation? 2. Always the highest exponent. In this case, degree is 2. Now, if a is greater than 0. Now let's think about what we're looking at here. We are now looking at a graph of a quadratic function, a degree of 2. So now we have to look at it and we got to say to ourselves, all right, what are some of the things that this stands out here? All right, first things first. How many x-intercepts are there in this equation itself here? There's 2. There is a possibility of 0, 1, or 2, 0, 1, or 2 x-intercepts for a quadratic equation. That one has 2. This one has 1. What do you notice about that one? Yes, it is the vertex of that graph. So when it has a degree of 2 and it has only 1 x-intercept, that means it's the vertex of the actual graph. Just throwing that out there. All right. What about this guy? How many x-intercepts are there? There's none. Okay. So we understand this, that there can be a possibility of 0, 1, or 2 x-intercepts for a quadratic function, also known as a parabola. Yeah? Okay. All right. How many turning points are there here? Yeah, there's just 1. The turning point is right there, right where the vertex is. Turning point is the change of direction from top to bottom, up to down. What's the end behavior here? First of all, sorry, my bad. What is the a value on that equation right there on the board? The a value is 1. That is a positive value, yes? Therefore, when a is positive, when a is greater than 0, what is the end behavior for a quadratic function? Where does that graph start? 2 to 1. It starts in 2, ends in 1. The left side of the graph is in quadrant 2. The right side of the graph is in quadrant 1. Correct. 2 to 1. Okay? So, things that we need to know. End behavior, 2 to 1. Number of x-intercepts, 0, 1, or 2. Number of turns. The number of turns, also interesting to know or to remember. The number of turns is always going to be 1 less than the degree of the polynomial. The number of turns will always be 1 less than the degree of the polynomial. Okay? What changes if I add the negative to it? It flips. What's the only thing that changes? Does the number of x-intercepts change? No, it's still 0, 1, or 2, correct? Okay. How many turning points? 1. Okay. Excellent. What changes? The end behavior. What is the end behavior now? 3 to 4. All right. So far, so good. Okay. Now, here's what I want you to also factor in. If the degree is an even value, you don't need to go this far, but I'm showing it to you anyways. If the degree is a 4 or a 6 or a 2, the end behavior still is the same for all of them. Okay? The end behavior stays the same. So you just got to remember that. 1, 3, 5, 7, 9, the odd ones, same end behavior for them. Let's have a look. Y equals ax cubed plus bx squared plus cx add d. What is the y-intercept for this guy? D. Okay, let's look at a excuse me. Let's look at a cubic function now. That's good enough. All right. Stink. Man. All right. What is the degree of that equation, please? 3. The degree is 3. How many turning points do you see on that equation? 2. Awesome. Degree is 3. Number of turning points is 2. How many x-intercepts are there in this equation? How many? 2. Okay. Can I have 0 x-intercepts? What's the end behavior of this guy? 3 to 1. That is the same end behavior as the line we started with today. And it will be the same for a degree of 5. The end behavior, if the a value is positive, is 3 to 1. So if it has to go from 3 to 1, that means it has to cross the x-axis a minimum of 1 time. Has to cross it a minimum of 1 time. Okay? So the number of x-intercepts possible is 1, 2, or 3. This one has how many? 2. Let me see if I can adjust this. Let's add 2. How many x-intercepts are there? 1. That didn't work. Let's hoping it would. Did not work. How many x-intercepts there? Still 1. Right? Okay. Means I'm going to have to adjust something in here. Maybe go 4x plus, there we go. How many x-intercepts are there? 3. 1, 2, 3. How many turning points? 2. So if you were asked to graph this, this is a cubic function. If you're asked to graph this, you always graph the x-intercepts and the y-intercepts. That's mandatory. If you're using Desmos, you also need the turning points. You want to make sure that those are labeled as well. Okay? So in this case, here's your 2 turning points, here and here. You would label those as well. In pre-calculus, they don't ask you for the turning points because you don't have technology to get them. And this one you do. All right. So end behavior, degree, turning points. The last thing that we need to look at is domain and range. Okay? So what is the domain for that graph right there? X is an element of all reals. It goes left forever, right forever. What is the range for that graph? Y is also an element of all reals. It goes down forever and up forever. Okay? Also the same as a linear function. All right? The parabola, on the other hand, let's have a look at that. This guy right there. All right. What is the domain for the parabola? This is a quadratic function, what is the domain for this function? How far left does it go? X and L of all reals. Negative infinity to positive infinity, yeah? Okay. What's the range for this guy? Beautiful. Y is all the Y values on the graph are up there, yeah? Therefore, that's the smallest possible Y value you can have. Therefore, the range is Y is greater than that. Make sense? Remember that?
Yeah.
Good job. All math is done. Break one hurt. It's a reflection of your teacher. Let's look at example 1 on page 158. Determine the following characteristics of each function. All right. What type of function do I have written on the board? Linear. What degree is that function? How many turning points does that function have? 0. How many x-intercepts does that have? Where's the y-intercept? 2. There's your y-intercept. It's always the value that doesn't have, it's the value that doesn't have a variable beside it. That's your y-intercept. Okay? And behavior of that graph before I draw it? 3 to 1. So same. There's all the information you need to know. What's the domain for that graph? X an element of all reals. What's the range of that graph? Y is an element of all reals. Any questions about it? Pretty simple run through on that. Okay. All right. I need to. Okay, I'm going to do the second example, and then I'm going to go through 6.3. I'm going to start it today. Okay. Negative 5x squared plus 2x subtract 1. All right. Let's go through all the information. First of all, what type of graph is that? It is a quadratic graph. Quadratic. What is the degree of that graph? 2. What is the y-intercept of that graph? -1. How many x-intercepts does that graph have? 0. How many turning points does that graph have? What is the end behavior of that graph? 3 to 4. Okay. So you were able to follow everything from yesterday by the sounds of it today. All right. Where did you get to yesterday? End of 6.2? Not all the way there?
2 questions on 6.2.
Sorry?
I'm gonna have to do 6.2.
You have not done 6.2?
Well, I mean, I did, but I have to finish 2.
Okay. Do you need help with them? Hey, you do? For questions?
2 and 4. But you can go through 6.3 first, because there's only 4 points in this.
Okay. Okay. Grab your phones. Put them in test mode, please. We have to figure this out. Yeah. I gotta figure this out. There we go. I need this. No. I need that. I need a quick YouTube video. How do I do this again? I need to. Okay. How do I get a table onto here? Open it. One second. I have to look on my phone.
Press the plus button in the corner.
Oh, right here?
Yeah, and press Q.
Ah, thank you. Okay, so we start with this right here. All right, now, there are 3 sections left. 3 sections left. In all 3 sections, you're going to do what we call regression graphs. And all a regression graph is you put in actual plotted points, and it'll give you the graph of best fit. That's all it does. Now, we used to do it on the TI-83 calculators, but we now have figured out how to do it on Desmos. You're more familiar with Desmos now this year, so we're going to work through it. So what I want to do is I'm going to put in my coordinates. So looking at the question, so we're going to model data with lines of best fit. So these are just the ones in 6.3 are going to be lines of best fit. So we need to put in the year in my X value. So the first year is 1964. Then I have 1968. Are we all in the same part here?
Sorry, no, what, yeah, how do you get a table?
That plus, it says table.
Yeah, what?
Is everybody there?
That's it, 1964.
1964, 1960. It's in the book on page 162, Nathan. 1972, 76, 1980, 84, Los Angeles Olympics, 1988, the Calgary Olympics.
Isn't it done now?
What's that, sorry?
Or do we keep going to the second row?
You go to the second row.
Oh, it is.
1992, 94, first year they changed the Olympics, 98, 2006, and 2010. Okay, so I've got that in. Now I'm going to go back up to here. I'm going to put in the times. So these are the winning times for the biathlon in the Winter Olympics. So 80.4, 73.8, 75.9, 74.2, 68.3, 71.9, 56.6, 57.6, 1994 is 57.4, 56.2, 54.3, and 48.4. All right, now, something I just learned this week as well. So everybody has those points put in?
Yes.
Okay, if you're looking where my 2010 and 48.4 are. What do you see to the left of it? Looks like a magnifying glass with a plus in it. You're going to hit that button and it should take you to the graph. What you see.
It took me to the graph.
Oh, yeah.
I did do that this time.
Okay, does your graph look something like that? Yeah? Is that what your graph looks like? Yes or no? Okay, well, what's kind of mean, Alex?
He's gonna go way up in the reserve.
Okay, well, we got 1922 in there. 1992. Okay, so we see that so far. Yes? Okay, now I need to do something here. Okay, first of all, that puts them there. Now I need to figure this out. Sorry, this is gonna take a second for me. I am looking to right here. Okay. What I just hit was up in this corner right here. Up in this corner, there was little dots with a line thing on it. Yeah? Okay.
Yeah, I had it.
All right. Now, how did you get to there?
Just did that on that.
Yours came up like that? Oh, right down here. Sorry. Okay, so have a look down here, please. All right, so what you need to know then is once you put the line in there, all right, first things first. What you have to do is you have to put that on your paper. You have to screenshot it and put it on your paper. Okay? That's what I say.
Like draw.
You just have to
Draw.
copy it.
Draw.
You don't like print it off.
Yeah.
You're taking the screenshot and you're going to draw it onto paper. Okay. However, this is going to change for you. We are working with polynomial functions. We may not have just linear regressions. So the other regressions are in here. It will tell you in the question which regression to work with. This one worked with a line. Secondly, most importantly, you must, Nathan, you must write the equation out every single time.
How did you get that linear thing?
It's at the bottom. Go down. Do you have a line on there yet, Nathan?
Oh, hit that all and it makes the line and then you just scroll down.
Yeah.
Oh, okay, I got it.
Okay. The equation of this graph, y equals negative 0.682x plus 1419.391. That equation will need to be written on every single graph you draw. And go to 3 decimal places, please.
Where does it like on the graph, like in quadrant 1, quadrant 2, does it matter?
Or you just write it.
Just write it anywhere on the graph, wherever you can find room. Okay? That is regression. Now, had I done this last year with you, we'd have been here for 45 minutes. Every one of you would have been in wrong spot on your calculator. And it's the most painful thing I can teach you. Because not one of you can follow instructions at the pace I need you to follow instructions at, Alex. Now, we just learned it all in 8 minutes. Okay? So you now are able to do this much, much simpler than anything we've been able to do before. Okay? All of 6.3 is on modeling a line of best fit. 6.4 is modeling a curve of best fit, which means it's either cubic or quadratic or possibly quartic, but I don't think there's any quartic. I think it's just cubic and quadratic.
So right when you press the line thing, it'll always bring a linear one and you have to change it yourself or like,
Yes.
Okay, so.
I shouldn't say that. I'm gonna say yes now, right now,
Okay.
but I'm not sure. It might change. Yes, go, Reese.
Like tomorrow, we won't be here, or like,
No, I know, you're not here the next 2 days.
so are we just gonna do 6-3 and then like figure out 6-4 ourselves, or?
Would you like me to go through an example?
It doesn't, like, I don't.
Okay, look up page 166. Okay, so let's start from scratch. I want you to hit the X on the top left corner, or sorry, the top right corner of that box. I want nothing in there right now. So hit the X on it so we know how to get to where we need to get to. So everybody is in that spot right now. You have a blank screen, yes? Okay. So first things first, plus sign, table. That's the first thing you do. Plus sign, table. Everybody's there? Okay. All right, let's enter in page 166. A pebble falls from a cliffside into the river 30 meters below. This table gives you the height of the pebble as it falls. All right, so put in the coordinates, 0 and 30. So 0 and 30 is the first one. Then I go here. 0.5, 28.77. Yeah. 1, 25.11. 1.5. And, oh, sorry, it's 1.2. Don't put 1.5, it's wrong, it's 1.2. 1.2 and 22.97. 1.5 and 18.98. 2 and 10.42. Okay, do not do anything. Do not do anything. Just please put those numbers in and don't touch another thing on that screen, please. Somebody always asks. Goes on your own.
Alex, heads in the
Like
air.
if it's
Heads in the
2.0,
air.
it doesn't matter if you put the 0, right?
That's correct. You need to-
Well, I was just adding zeros.
Everybody's there now? Okay. 2 things that we got to do now. All right? We probably can do them. It doesn't matter the order in which you do them. Let's first see the points on the graph. So hit the magnifying glass right here. So now I have points that look like that, yes? Put up your hand if your points don't look like that. Your points don't look like that, Alex?
No,
All right, now I need the line. So this is a curve of best fit. What does that look like to you? Does that look like a straight line? No? What would you think the regression graph should be here? Quadratic? Okay, so let's see what happens when we actually hit the lines up there. Now, it did not switch for us, so that's a problem. So we got to know what it is. Well, in the question, it'll tell you what it is. It was a quadratic regression. There is the equation of the line. Now, if you were to graph this yourself, first things first, I need you to listen. Can we have a negative time? No. So we don't need the negative part of that graph. You only graph the first quadrant. Okay? Second, what do we have to make sure we do? Write the equation on the graph. So you write the equation on the graph. Okay? That equation, y equals negative 4.902. All right,
You said to move the decimals to this, right?
yes, please.
No, we have to label like all the points or not what?
No. You, well, sorry, yeah, I would label all of those points
So.
that they give you. Now, having to look at this graph, this doesn't and shouldn't happen, boys. This shouldn't happen. The line does not go through all of the coordinates. It's called a line of best fit. It goes through the average, so to speak, of the coordinates. Okay? So it won't necessarily go through all of them. So you do not have to connect them like that. You just put the arc through them so that it looks like it goes through the middle of all the coordinates. Okay? You'll see as you go through these questions what that means. But like I said, I just gave you chapter 6, all of it in 45 minutes because Desmos makes it that much easier for you. Yes, Reese. Well, let's see how far we can get. No. You,
I mean,
I have to know what I say, right? And biology.
okay. However, what I need you to understand is we are going to try and wrap this up midweek next week. Because I want to do our best to get through 7 and 8 if we can before break, before Christmas break. Because I want to then only have to do design and measurement and study for your provincial exam after the break, if we can help it. Yes, Aaliyah?
A lot of us will be here Wednesday and Thursday.
Oh, yeah, we have a like all of them.
Okay.
what?
The assessment will likely be on Tuesday on this then.
You'll have to deal with us. Yeah, you got me and Nathan.
Assignments or tests?
Or do just tests.
I don't know what we're gonna do. I will let you know Monday.
Is it not gonna be
I
Monday?
put assignment too. Yeah.
Well, no, it has to count for marks.
It has to be just a test.
So it's gonna be one of the. Cohen, can you stop talking when I am, please? All right, go ahead.
When we're doing this on our, like drawing it, do you also want us to label the x axis and the y?
Yeah.
With intercepts?
Intercepts, yes. Yes, that's a great question, Summer. You do want to make sure that your y and x intercepts are labeled when doing these.
And even though like you didn't just like in the first quadrant, you still put on arrowheads, right?
No,
No?
that's a great question as well. You do not put arrowheads on graphs that are not continued. This graph does not continue into negative time, so you don't put an arrowhead on it. On the first two sections that we do, 6.1 and 6.2, they all have arrowheads on them because they are continuous graphs. But when you're doing a question such as this, where there's an actual definitive amount of something, and it might only be positive, you don't put arrowheads on it, you just put it in the quadrant where it is. This can hit the water. So one of the questions that you will be asked, when does it hit the water? 2.47 seconds after it's been released. So those are the types of questions that you'll be asked to do. This section should take you basically 4 days to finish at most. Like there's not a lot to it. Yeah.
And when we're on the graph, like, do we have to like do the numbers or can we just like do the one number? You know what I mean?
No.
We don't care. You don't know what I mean?
No.
Like how it's like 0.5, 1, 1.5, 2, 1.5. Like do we have to do that or can we? just
No,
do, like, the final one?
no.
Oh.
No.
Like I don't know how it's specific.
No.
You just draw the lines, draw the points.
Yeah, they're not even giving them to you. Okay, so if you have the table,
Like I meant like if we figure out to like a
Yeah.
thousand.
yeah, no, you don't have to. Any other questions about this here? This is regression graphs. Okay, where did you wanted what?
6.2,
What page?
number, 161, number 2.
Okay, write a polynomial function that satisfies the set of characteristics. So it extends from 3 to 4 with one turning point and a y-intercept of 4. Okay, so of all of these, which degrees are 3 to 4? Which ones have an end behavior of 3 or 4? Yes, quadratic functions that are upside down. You're absolutely correct. But there's another thing that could have told you this. The number of turning points is 1 less than the degree.
So it's square.
So it's squared. So it's a quadratic function. So you write it out like this: y equals ax squared plus bx plus c. Now that's what we start with. Now, we need a value for a, b, and c. Got me?
Yeah.
Okay. Because it's quadrant 3 to 4, that means it starts here and finishes over here. What does that tell you about your a value? Is it positive or is it negative? All right, so I have y equals x squared. What's the end behavior of that guy? Right, but that's not what that asked, is it? It asked you for what?
From quadrant 3 to 4.
So then what does that mean the a value has to be? Okay, so that has to be there. Yes. Got me so far? All right, so first thing I do is I put a negative in here. All right. Says it has a y-intercept of y-intercept of 4. So what part of that equation is the y-intercept? So then I have to have a 4 here. I could leave it like that if I want. Or I can put a b value in. It doesn't matter. It's just saying like you can put whatever numbers in you want to create an equation. There's an unlimited amount of equations. It's an infinite amount of equations.
Like obviously it's 4 and then it has to be negative and then you can just go like negative 2 squared plus 5x.
So what does the b like do? Like even in like the
Excellent.
cubic one, like it's such a long equation, like what are all
Okay,
those?
let's look at that because that's not a bad question. Okay, so x squared plus 2x subtract 4. Okay, so this is my graph here, right? Okay, let's adjust b and see what happens. What happens to the graph?
Shifted left.
What?
Shifted left.
Did it?
Or,
Why are you supposed to be
yeah. I mean, it might have done something else, but it also went.
Okay, this one's -1, -5, yes?
Okay. Or a straight line.
This one is -2.5, -10.25. So it actually moved the graph, it made the graph bigger by the looks of it. Wider, shifted a bit. So the b value does multiple things, but it's the least important that you need to know because we don't care. We only care about a and c. Okay.
So what about for the cubic one, like there's 2 different,
Where are you?
like just in general, like the cubic equations, like a x cubed plus cx squared plus cx plus
Mhm.
so like the 2 middle ones aren't important either.
No.
Okay.
Okay, so I answered the first part of 2. Do you need me to go through the rest of 2? B, C, and D?
No, but
Three?
when it's like it can be when you have A, B, and C, it can be negative. You don't have to, oh yeah, degree B, right? Like subtract
Yeah. Oh, yeah.
C. How do you like know that?
You don't. You put whatever you want for it. It doesn't affect,
The first one.
C affects the y-intercept, A affects the end behavior, and whether the graph would go up or down. That's what A affects. B, we're not concerned about the effects of B, that's what I was just explaining. to her.
Oh, okay.
I don't care what B matters. Yes, you can put whatever you want for it. It doesn't change what the question's asking. It doesn't change the number of turns. It does affect what the x-intercepts are, but we don't need that just yet.
Can you like put a negative 5? Let's see what it looks like on the graph.
A negative B?
Negative 5.
Sure.
Yeah.
Oh, it just
So
goes to
in the
the
y
other
is
side.
Move that one to the right.
No, it'll be y has to be greater than or equal
Weird, eh?
to that.
Yeah.
Okay, let me show you something.
That is the bathroom.
Actually, this question actually works out. That equation I picked was accidental, but it actually is going to work out well. That's what I have right there, right? Okay, I want to show you something. Find the x-intercepts of this graph. I put y in for 0. 0 in for y. 0 in for y, because along that axis, y is always 0. Along that axis, the y value is 0. Along that axis, y value is exactly along the axis.
Can you make sure all your
The
numbers are
x-intercept is found when y equals 0. That's what I'm trying to tell you. Okay? So to find out what the x-intercepts are, so my x-intercepts for that graph are 4 and 1.
The thing.
Oh, I had to put it this way. So there's my x-intercepts there, right? Now, if I change b, the whole thing is going to shift. So that's no longer my x-intercept. So that's what b affects. B affects what the x-intercepts are. Well, again, it's not imperative that we know that.
And the first one.
Okay, so I just changed that. So now my vertex also changed. So everything does shift because of b, but it's not something that we focus on to find any degree, turning points, x-intercepts. We don't use it.
Do we have to know how to spiral for the x-intercepts from the first one?
Using the graph, yes.
Just the graph.
In pre-calculus, you have to solve for them.
No. Oh, yeah, I did.
Okay, summary, you would have to use just 2. Is that all you needed?
Yeah, I
And four.
4?
Did you not?
I got the same two.
Did you get it?
Okay, so basically, because you could just, now that you know what you know, what you can do is you can just put the equation in. Yeah. And then define whether it's equal to 1,000, then you can put, you can find out, you can use your cursor to go into there, or you
How
can.
do you do that?
So that takes care of that.
No, but like, it's, yeah, I can tell you, but like,
Oh, look on here, 1996.
like, if you, it's, I'll just tell you, it's linear.